All right, so I'm not exactly sure who showed up for the problem session on Monday, but I hope it went well. I was talking to my TAs, and it might be possible to offer 2 problem sessions. So for those of you that can't make it to the one on Mondays from 4 to 5, there are 2 options. So one would be today, so Thursday, from 4 to 5 as well, or Friday from 2, but that one would have to end early because Micah has to get to a lab or something like that, problem session. So it would be from 2 to like 2:45. So that would be a little bit shorter. But if more people can make it to that one, then maybe we want to do that one. So for those of you that can't make it on Monday and do actually want to go to the problem session, could you just like type in the chat what you would prefer? Okay. Thursday. Okay, cool. So, Friday. So I'll let everybody have a chance to. I don't know if anyone just joined. Okay, so hopefully everybody heard. Maybe I'll mention it again at the end of class to make sure that can't do either. Yeah, that's unfortunate. It's really hard to find a time that works for everybody. Okay, so we'll set that at the end of class. Remind me if I forget so that I don't know. Let's see. We are okay. Oops, there we go. Try this. We are finishing up with 1.7, which is linear independence. So we went over the definition, right, of linear independence. This is a property of a set of vectors. So let's just go over the definition just to refresh our minds. So a set of vectors v1 up to vk is said to be linearly independent if when we write down this vector equation, x1 plus times v1, x2 times v2 up to xk vk equals 0, this has only the trivial solution. Right? Meaning that all of the x, or we could write it this way actually, equals 0. So each of them equals 0. This is called the trivial solution. Okay. And we went over an example of how to figure out whether three vectors were linearly independent, and we can do that by just creating an augmented matrix and solving it, right? So this is what we've been doing up to this point. So it's just another application of solving systems of linear equations. Okay, so let's see. There were some remarks I wanted to make about this, about linear independence. So first of all, 2 vectors. So if you're just focusing on a set with only 2 vectors in it, and we'll call them u and v. These are linearly independent. We'll say linearly dependent. If and only if one is a constant multiple of the other. Right. So if we have U, it looks like this. Then if V is linearly dependent, if U and V are linearly dependent, that means that V has to be something along the same line, right? Or it could be, going in the other direction, but a constant multiple of that vector U. And so another way of saying that is that if you're given U, V is linearly dependent with U if and only if V is in the span of U, right? So there's a relationship between this linear independence or dependence and being in the span of the collection of vectors, right? Okay. All right. Also, if you have a collection of vectors that includes, or so if this includes the zero vector, so if one of these VI's are the zero vector, then your collection is linearly dependent.
So it's always linearly dependent.
If it has zero, yes.
Okay.
And that's because the zero vector will necessarily be in the span of any VI.
Yeah, that's one way of thinking about it. Yeah. So another way to think about this is just using the definition. So if, say, V1 is equal to 0, and if it isn't V1 that's equal to the zero vector, then you just shuffle them around until V1 is until the zero vector is at the front. And once you have this, you can choose your x1 from that linear dependence equation. So this thing right here, we're creating this. Choose x1 to be 1 and all others, or I'll just put it this way, and all other xi to be 0, right? And then your equation becomes 1 times v1, which is that 0 vector, plus 0 times v2, plus 0 times vk, and equals 0. So you can see on the left-hand side, all of these will just collapse to 0, and 1 times v1, which is the 0 vector, will be the 0 vector. So 0 vector on the left-hand side, 0 vector on the right-hand side. So this is satisfied. And this is not the trivial solution. This is so 1 and then followed by all zeros is a non-trivial solution.
And that's just one of the non-trivial solutions, right? You could have a different number like 2 or...
You could, but you might not. So since you don't know anything else about the V1 up to VK, except that V1 is equal to 0, they might be linearly independent if you pop off that 0 vector. But because
what I meant is like the scalar for the V1. If we know that V1 is 0 vector, then that scalar could be anything, right?
Right, yeah, it could be anything.
That's...
So long as it's not 0. Right. Because then if it was 0, it would be the trivial solution. What if more than one vector is the 0 vector? You get the same thing. Yeah. So if you add the 0 vector like several times, then you're still linearly dependent, right? Okay, so one more thing I wanted to say was that if you have a collection, so starting with two vectors u and v and a vector w that's in the span of u and v, then this collection where you just add w, this will be linearly dependent. Okay, so it's saying that you start with a collection, you add one that is in the span of that collection, then you get something that's linearly dependent, right? And more generally, if you have a collection of, say, k vectors, and you add a vk plus 1 that's in the span of v1 up to vk, then maybe I'll put an if in here. So if this is in the span, then the collection of v1 up to vk and then adding vk plus 1 is linearly dependent. Okay. Okay, so adding that one vector that's in the span creates a collection that is linearly dependent. Another way of thinking about this is that, so this is the same idea, but just put it a different way. If you have, say, two vectors, u and v, so if this is linearly independent, and you want to add a vector, w, oh, oops. So if this is linearly independent and you want to add w and have this collection UVW still be linearly independent, then W must not be in the span of U and V. You just have to choose something outside of that, right? If you want to maintain linear independence. So just visualizing this, so say you have two vectors U and V and they span a plane, right? If you want W to be in this collection and maintain linear independence, then it has to be somewhere outside of the span. Then you can add that vector and not change linear independence. Okay. So,
I didn't mean, oh, sorry.
Okay, go ahead.
I'm curious for the graph. I guess, is there a way to know visually if something is in the span of U and V or not?
Well, okay, we can visualize it in R3. And if you have two vectors, then so long as they are linearly independent, so not constant multiples of each other, they will span a plane, right? So that's,
Okay, cool.
yeah, what I've drawn here. So you can imagine this, like, or maybe I'll do it in, yeah. So they create this like plane, and you just choose W to be outside of that plane.
Thank you.
No problem. Okay, so something that's pretty useful for thinking about this and answering questions like whether a collection of vectors is linearly dependent or linearly independent is to think about it in terms of a matrix, right? So given a set of vectors, V1 up to Vk, we can form a matrix where we just stick V1 up to Vk into, so those will form the columns of this matrix, right? And then, so I guess I'll write it this way. These vectors are linearly independent So I'm going to use this notation that's, I don't know if I've talked about this before, but this like double-sided arrow, this is like shorthand for if and only if. So I'm saying that this statement is equivalent to what I'm about to write next, which is that AX equals 0 has only the trivial solution. So this is really similar to how we defined linear independence. So the next thing that I write is actually the more useful thing. So this is, when I write this again, I mean that all of these things are equivalent. So hopefully that part's clear. So this statement, this one, and the one I'm about to write, which is that A has a pivot position in every column, which means that we take A, we row reduce it, and then we check that there's a pivot in every column. And that will tell us whether this collection is linearly independent. If we have a pivot position in every column, we have linear independence. Otherwise, we have linear dependence. Okay, so this is the most practical way of checking, right? Linear independence. And so just to visualize this, if you have say a matrix that has some pivots, say it's something like this, right? Okay. So this does not have a pivot position in every column, right? We have one pivot here and one here. And this is going to have a free variable. So if we have a free variable, then we don't have only the trivial solution, right? So that's really what this last statement is saying. We get a free variable if we don't have a pivot in every column. If I'm missing a pivot in a column, and then that will give us solutions apart from the trivial solution. Okay. And knowing this, we can actually say something about a collection of vectors. Say we have V1 up to Vk, and these are vectors in Rn. And suppose, so if this is the case, and K, so our number of vectors is greater than the dimension of the space that they're coming from. If that is the case, then we must have that V1 up to Vk are linearly dependent. And the reason being that if we, so just as an example, if we had the vectors 0, 0, or yeah, 1, 0, 0, 0, 0, 0, 1, or yeah, this guy right here, and then some other vectors after that, doesn't really matter what they are, right? So here our vectors are coming from R4, but we have 6 of them. And when we have more columns than we have rows, we can't possibly have a pivot in every column, right? So we end up with these free variables, which again give us a non-trivial solution. So we can't have linear independence, right? Okay, so another way of thinking about this is that there's not enough room in your space for there to be k linearly independent vectors. Sorry, there's not enough room for there to be k linearly independent vectors if you have k being larger than your space. And if you're thinking about this in terms of this span, that also makes sense. You can't span something, you sort of run out of room, right? You span the whole space and then you have no more room to have another linearly independent vector, okay? All right, so there's a few different ways of thinking about this. Yeah, this is linear independence. We'll be coming back to this. So yeah, hopefully we'll get used to it eventually. Okay, so if there are no questions right now, I'll move on to 1.8. And does anybody have a question? Not right now? Okay, cool. Let's see. So this is the next section, and we start talking about linear transformations. Move this down just a little bit. Okay, so before we really start talking about what it means to be a linear transformation, I think we should first talk about viewing a function in this sort of different way. So linear transformations are functions. So first of all, these are just functions with a special property. And we're kind of viewing functions differently than maybe you have done before, right? So our viewpoint is going to be of a function as a mapping or a transformation. Okay. So you usually would think of a function, so this is, or maybe in prior math classes would think of a function as like something like this, f of x equals x squared, right? You have a formula, you have input, output, and you would think of the graph of this function, right? You know, this graph. Or, you know, if you have done stuff in 2 variables, maybe you've seen these types of functions where your input has two variables and then your output is something like this, right? X squared and y squared. And you know that these functions have a domain and a range, right? So in this case, so just separating right here, you have a domain that's just R, and the range for this particular function is 0 to infinity, right? And here, the domain, since it's x and y, our domain is R2, and the range, this actually can only have positive values in each coordinate, so your range will be 0 to infinity, cross 0 to infinity, or another way of thinking about this is the first quadrant of R2. So. Great. Okay, so right, so you should be familiar with all of these. These feel hopefully normal and natural. But what we want to do in this class is, instead of really thinking of a function as something like this, where we're looking at the graph, we're visualizing both the domain and the range at the same time, you want to split them. So you're really thinking domain on one side, your range or codomain on the other, and you want to imagine your function moving between them. Okay, so I'll draw that picture in a second. So I just wanted to mention what I mean by codomain. So there's another thing called codomain, and that is just the space that you so this is how I would put it, the space where your function values live. Okay, so this is where your values end up. So when you plug in an x into f, you get a number in R. So it's just the space where your function values end up. So your codomain in this case is R. In the second example, we had a coordinate pair, and so these will be domain. This space is R2, right? So it's not really caring about what points get hit. It's really just saying the space where they end up is R2, and I don't really care whether it's all of R2 or some subset, right? Okay, so that is the codomain. I also like to call this the target space, because I think that's a little bit more descriptive, but I think the book uses codomain, so it's good to know that. Okay. So one thing to note is that the range is always a subset of the codomain. It could be the entire codomain, but in general, it's a subset. All right, so now this view of functions. So thinking of separating the domain and codomain. Right, so say I have a function from Rn to Rm. I'll just draw them like this. So they're both going to look like R3, but that's just imagine arbitrary dimension here. Okay, so I have a function, and on this side I have my domain, right? And on the other side I have my codomain, right? And if I have a vector here, so say I have this vector u, I imagine that f acts on that vector. So f takes that vector u and sends it to the other side, and we end up with its image over here, which is f of u, some vector in Rm, right? So everything on the left-hand side gets mapped to something on the right-hand side. And remember, that's the definition of a function, right? So every input has an output, right? Unique one. Right. So in this case, we can say that f maps or sends that vector u to f of u, right? And then this is what we would refer to as the image of that vector u. Okay, so all of this language is gonna help you envision the function in this way, right? So as a mapping, it takes one vector and maps it to another vector in the codomain, right? Okay, And this is really like an important idea. And maybe it doesn't feel so important because you're used to functions and everything, but thinking of functions in this way is a lot broader than maybe you've thought of them before. And it's really how, as mathematicians, we want to be thinking about functions, right? This is the proper way. It's more general. It allows us to think of more like examples, interesting examples of functions. Okay, and especially it's the proper way to think of them in this class. Okay, some notation that we'll be using. So we can write F, Rn, and then an arrow and Rm. And what we mean when we write this down is that F is a function. Its domain is Rn, and its codomain or target space, is Rm. So it is mapping Rn into Rm. Right? And so this really encodes all of the, so it encodes some important information about the function, right? It tells you what the domain is and what the codomain is. And it's really useful for, so when we write down a function in other classes, we oftentimes don't even tell you what the domain is, and it's sort of implicit or implied, right? So in this class, we want to be very explicit about what the domain of the function is and where it's ending up, right? Okay, so this is the notation that we'll use. And now let's finally define what it means to be a linear transformation, right? Okay, so a mapping or transformation T, so we usually use T for a linear transformation, T standing for transformation. So a transformation T is a linear transformation if you have two things. So the first is that T applied to U plus V is equal to T of U. Make that look more like a U. Plus T of V. This is for all U and V in Rn. Oh, oops. And number two is that T applied to a constant times U is equal to that constant times T of U, right? For all vectors U in Rn and constants C, right? Or scalars. Okay, so this is what it means to be linear, right? So this is a linear transformation. And it's good to note that these conditions, so these two things, they're very strong statements, right? They're not satisfied by a lot of functions. So many functions do not satisfy this. So let's look at some examples. So these are non-examples because these are not linear transformations. We'll do plenty of examples of actual linear transformations, but first. So let's look at a function just from R to R, right? So that is described by this formula. So this is just square root of x. This is a familiar function, right? If we look at sorry, the image of c times x, so we just multiply by some scalar c, then we'll get the square root of c times x, right? And this is not equal to, pulling out that constant, right? We can't just pull out a constant from a square root, right? And so this is not what this is, c times t of x, right? If we just plug back in t of x for square root. And so this is not a linear transformation. So you see that like pulling out a constant is not something that you get out of every function, right? So it's actually a really nice property to have. Also, another example. So this, just to be really clear, this is not a linear transformation. Another example would be, so let's say our domain is R2, mapping into R, and say this is given by, so it will take a vector, use x and y, and its image is just x times y, right? This is also not linear, and we can see this by looking at c times that vector x, y. We know that by how multiplication by scalars works, we just multiply each component of that vector by c, right? And then if we look at what that is using the definition of t, that's cx times cy, which is c squared x times y, right? Which is not what we would get if we plug in just a standard vector, this x, y, and then multiply by c. So this is not equal to c times t applied to this vector. So again, this is not a linear transformation. And finally, so you might guess that, well, are, linear functions, linear transformations, like the lines that we know about, y equals mx plus b, like, is that a linear transformation? And it turns out that sometimes it is a linear transformation. So if we look at a function r to r, that is, so for example, 5 times x. We can check, and this is not a non-example, this is a true example of a linear transformation. We could check this by looking at the sum of two, well, these are not vectors, these are just real numbers, but the sum of these two, and just using the definition of t, this is 5 times x1 plus x2, which is, we just distribute 5x1 plus 5x2. This is the same as t of x1 plus t of x2. So we can split sums, right? That's the first property. So this is property 1. And then we have to check property 2, which is that we can pull out scalars. So if we take an arbitrary scalar, so c is just some number times x, that is 5c times x. And we can interchange c and 5, right? We get c times 5x, which is just c times t of x. So we get both properties, right? So t is a linear transformation. So note, if we were to take t and add a constant, so 5x plus 1, this is also the equation of a line in R, right? Well, in R2, technically, but this is not a linear transformation. right? Okay, so the key is that here we did not have something plus a constant, right? We just had that scalar times x. If we add this plus 1, it does screw things up. So if we look at, say, I'll give this guy a little hat. This is not a linear transformation. X1 plus x2, and we just evaluate this, we get 5x1 plus x2 plus 1, and we get 5x1 plus 5x2 plus 1, and then we get here, this would be actually t of x2, but this is not t of x1, right? So we don't get that we can split sums. I should put the hat on this guy too. And so that's really the issue. So this is what we would actually call an affine transformation. I'm not sure that we will talk about these again. Maybe we'll talk about it towards the end of the class, but really these are the only functions. So lines that go through 0, 0 are linear transformations, otherwise not.
So just a question, are there like transformations that like only satisfy one of these two conditions?
Oh. In theory they could, but I'll have to think about that.
So usually if one of these conditions is not satisfied, then it's, I mean, if one of them was satisfied, then the other one would be?
I'm okay, let's see. If we have, say, like, yeah, I think this one would satisfy. So if you take x plus y, that's, ooh, that doesn't work, no. Okay, it would be, okay, I would have to think about that. There may be something that satisfies one and not the other.
So it's just always a good idea to check both, right?
Yes, yeah, it's a good idea to check both. We'll actually have a characterization that will make it less necessary for you to, check these conditions. And we'll see if we get to that. Right. Okay, so this is one side. Okay, I'll get back to you on that question, see if I can think of something. Okay, so we're gonna do some more examples. Let's see. So here's an example from R3 to R3, linear transformation. And this will be given by, so we'll have t of a vector x. We'll just send this to x1, x2, 0. So it leaves the first two components alone and sends the third one to 0. So what this does is, if we imagine this in R3, and it's a little convenient in this case to think about this in the same plane or in the same space. So it would take this vector here, maybe I'll draw this a little bit better. Okay. This vector, so an arbitrary vector x, would be projected down into the xy, or not xy, I guess x1, x2 plane, right? Right, so this is what we would call a projection. Let me so think of this just being collapsed down, right? Because we collapse that third coordinate. So we might say t collapses the third coordinate, and t is called a projection. And you can check that it's linear, right? So I guess why not go through that? If we have, say, x1, x2, x3, and y1, y2, y3, then this will be, first let's just combine them. So x1 plus y1, x2 plus y2, x3 plus y3. This will be, the image of this is x1 plus y1, x2 plus y2, and the last coordinate is 0. Then we can split those into two vectors. So we would get x1, x2, 0 plus y1, y2, 0. And that is t of that. I'll just write this as x, right? T of x and, oops, plus t of y. So this here is x, this is y. Okay, so that's the first property. Second property would be t of a constant times x1, x2, x3. And hopefully, I guess we'll finish this off, but hopefully this part is clear, right? We just do this, apply t, which deletes the third coordinate. So we get cx1, cx2, 0. And 0, we can also see as being c times 0, right? So we can pull that c out and get x1, x2, 0. And that is c times t of x. This is, so first property, second property, so t is a linear transformation. Okay, so let's talk about two properties that linear transformations have, which come directly from the definition. So if t is a linear transformation, then we get, let's see, then t of 0, so t of the 0 vector is equal to the 0 vector. And another way of putting this is that t sends 0 vector to 0 vector, right? Where if t maps Rn to Rm, these are actually different 0 vectors, right? This one would be in Rn and this one would be in Rm, but we use the same notation, right? Okay. So this just comes from that property about scalars, being able to pull out scalars. And so this is, so why is this the case? Because if we take t of 0, so 0 is a scalar, times, oops, some vector x, then when we multiply x by this scalar, it will be, so maybe I'll do this on this side. It'll give us the 0 vector, so just make all of the entries 0. And then we also have that property where we can pull out a scalar, so t of 0, this is equal to 0 times t of x, right? And that is, this is just a vector, and we multiply all of its entries by 0. So again, we get the 0 vector. And so this means that t of 0 vector is always equal to 0 vector. Right? Okay. So that's good to know. And also, we can consider applying a linear transformation to a linear combination, right? So this is where we take some scalars times vectors, right? Something like this. And from the fact that we can pull out constants and we can split over sums, we actually get that this is equal to C1 T of V1 plus C2 T of V2 all the way down to CK T of VK. Right. So what this means, so remembering that this is what we called a linear combination. There we go. So we take a linear combination, we apply our linear transformation, and we get a linear combination on the codomain side, right? So what we can say is that a linear transformation it behaves nicely with respect to linear combinations. So where nicely means we can split over linear combinations. Okay. All right. So there's a particular form of linear transformation that is really nice. So let's look at that. So we can create transformations of the form by taking a matrix and multiplying it by our vector, our variable in this case, right? So of the form A times X, where A is an m by n matrix, these are actually always linear. Okay, so any matrix we can come up with, we can form a transformation by doing this, and it will always be linear. And this just comes from the properties of matrices, of multiplication of matrices by vectors. So why is this the case? This is because we know that if we look at two vectors and our transformation is of this form, that means that this is just A times X plus Y. And it's one of our properties of multiplication in this way that this is equal to A times X plus A times Y, right? Which is just T of X plus T of Y. And then the same thing goes for multiplication by scalars. So when we have something like this, this is A times C times X. And this was again a property that we talked about before. So we can pull that scalar out, and this is equal to C times A times X, which is just C times T of X. Right. Okay, so this is a really convenient way of just creating linear transformations, right? So we can think of lots of examples now. It won't be hard to come up with them. I don't think I want to mention that. Okay, so let's do some examples. Are there any questions at this point? Are things good?
Yeah, so what exactly would the transformations of, is there like something that the transformations are used for? Is it just like, do they just basically replace functions and utilities? So like,
you mean like what are linear transformations good for, or?
Yeah, so like,
Do
they just kind of exist as something to be played around with, or do they have some sort of use?
They are very useful. So how do I say this? I guess okay, being an analyst, the first thing I think of is like calculus. Like in calculus, you have you define these like derivatives and also the tangent lines, right? And you use tangent lines to approximate your function. So in higher dimensions, you actually get not a tangent line, but something that is described using a linear transformation, right? So your analog in higher dimensions is really like using this idea of linear transformations, and you will like approximate your function using those. And it's because linear transformations are so nice. They behave really nicely. It's easy to do like approximations and calculations. And so if you're worried about like computation time or something like that, it's much better to use a linear transformation to approximate your function than deal with your actual function. Right?
Got it.
Yeah. Okay. So hopefully that's satisfying enough.
So it doesn't, like, it has more of an outside use than like,
I mean,
like it relates to other things alongside some other stuff within the realm math that we're learning currently.
Yeah. So that is part of why it's so useful. And it's also going to be important to us in this class. They are, sort of our most important functions. I think the only ones we'll talk about, honestly. So yeah. Okay, so let's look at some examples. Here we have, okay, knowing that we can just create a linear transformation by writing down a matrix, we're going to focus on R2, so functions from R2 to R2. So say we have this matrix times our vector x1, x2. So we can compute what this would be by just doing the matrix multiplication, and this would be negative x2 and x1, right? Okay, now it will be useful to visualize this by looking at just what happens to the unit square in R2. So we can visualize this transformation T by looking at what happens to the unit square. And we'll just introduce some notation that will be useful. So we're going to use E1 to denote the vector 1, 0, and E2 to denote the vector 0, 1. Okay, so looking at our plane in R2, right? These are just your unit vectors in the coordinate directions, right? So here's E1, here's E2. We'll have a more general definition in a little bit for higher dimensions, but it's basically, this is what it is. Unit vectors in the coordinate directions. Maybe I'll write that down. So these are and so what I mean by coordinate directions is really just like in the direction of the axes. Okay. So how are we going to use these to visualize our transformation? So our transformation goes from R2 to R2, right? I actually need a little bit more space, so here we go. And so let's say, all right, we have 1, 1 right here, right? Our unit vectors, E1 is right here, E2 is right here, and we're just looking at where those two vectors end up, right? So we can just compute that. T of, let's write it out. E1, which is 1, 0. We just use our definition, so this guy up here, and we'll get 0 in the first coordinate and 1 in the second coordinate, right? Right, yeah. So the image of E1 is going to be the vector, let me mark this off. So this is 1, minus 1.
Pardon me.
Yeah.
I'm a little confused as to how you're doing T of 1, 0 equals 0, 1.
I'm using this formula up here. So if you have x1, x2, it ends up being minus x2, x1.
Okay, thank you.
Okay, cool.
Sorry, I was making it more complicated than it actually was.
Right, yeah, that's fine. Okay, so that's our image of E1. And then we can also compute E2, which is the vector 0, 1. And using our formula, we would get -1, 0. Right? So our image of E2 is is right there, right? So what it looks like what happened is everything was shifted, like rotated 90 degrees, right? It took our unit square here and rotated it this way. We can do one more vector just to verify that, just to see if what we think is going on is actually what is going on. So let's do that. Okay, so let's look at this vector, which would be E1 plus E2, right? If we add these two together, using our, tip to tail or parallelogram rule, that is what we would get. So this is actually the vector 1, 1, right? If we want to look at what happens to that vector, so it's actually, we could compute it directly, or we could use the fact that this is a linear transformation, which is fun. So why don't we do that? So this is E1 plus E2. We know that that is T of E1 plus T of E2. And we already computed these. So the image of E1 is 0, 1. The image of E2 is -1, 0. And then we just add these together. We get -1, 1. Right? And then on our picture, so we would get -1 for the first coordinate and 1 for the second. So it ends up being right here. Straighten this up just a little bit. Okay. Let's see. So if we wanted to describe this linear transformation in words, we would say that T rotates everything by 90 degrees, just rotates everything. Okay. And the reason we know, so we know what it looks like for the unit square, and it's really the properties of being a linear transformation make everything else work in the same way. So it's really a rigid map. Like there's not a lot of wiggle room or like chance for it to behave differently. Okay, so we get the unit square gets mapped to this guy over here. Okay. So that is our first example. Let's look at another one. Are we doing on time? Okay. So this is the map, which will also be from R2 to R2, given by, how did I write this one? Okay. Taking x1, x2, and multiplying by this matrix. So 1, 0, 1, 1. Great. And then we can compute what this would be. So this would give you x1 plus x2, and then x2 in the second coordinate. Okay, so we want to do the same thing where we're going to look at the image of E1 and E2, right? So we have our two unit vectors. So I want you guys to try this on your own. So try and draw the picture sort of following the same procedure that I used for the first one and see what it looks like. Okay, does anybody want to describe what their transformation looks like? Or what the images of E1 and E2 look like?
I think
I'm not-
E1 is the same.
The
which is-
image of E1, yeah, is the same. Right, yeah, so E1 gets mapped to E1 on the other side. Does anybody want to say what happens to E2?
It's a like 1-1, like a 45-degree.
Yeah,
That's what I got too.
good. So you get this guy right here for the image of E2. And all of your vectors that are in the unit squares, so everything right here, will get mapped to a parallelogram, actually. So you could figure this out using the fact that this is a linear transformation. So it does make, so for instance, T of E1 plus E2, just thinking about this geometrically. So E1 plus E2 would give us the vector right here. This should be equal to T of E1 plus T of E2, which is the vector right here. If we think about vector addition geometrically, right? Okay, so we get a parallelogram. So our square gets pulled to the right in this way. So this is actually called a shear transformation. Yeah, so this is an important example of a linear transformation. Okay, now looks like we will be able to get to this. Cool. So one thing to notice is that, well, let's just focus on this example here. So I didn't write this down, but if we look at T of E1, what it is 1, 0, and T of E2 is 1, 1, right? And if we look at this and compare it to our matrix that defined our linear transformation, so that's this guy up here, notice that T of E1 matches up with the first column, right? So, right, anyways, yeah. This matches up with the first column, and then E2, T of E2 actually matches up with the second column. And this is something that is going to, so this is a pattern that will continue, right? So we can also check that in the first example, when we look at T of E1, that matches up with the first column of our matrix, and T of E2 matches up with the second column of our matrix, right? So notice that if we look at the matrix A, we can form it by using the images of E1 and E2 as the columns, right? In these two examples. And this is actually the case if we define a matrix transformation using a, if we define a linear transformation using a matrix, then this is what will happen, right? So we can write this down in a theorem. Right. So if T is a linear transformation, then okay, so yeah, I think what I said is not exactly what I was trying to say. So what I'm trying to say is that if we have a linear transformation and we form a matrix using the images of these unit vectors as our columns, then we get a matrix that describes it. So if T is any linear transformation, then there exists a unique matrix such that T is described by it, basically. T is equal to that matrix times X. Okay. And we know this because we will just form A by taking each of the columns to be T applied to those unit vectors. This would be N. Yeah. Okay. And so that's how we'll find the matrix, and that's how we'll know it exists, right? Okay. So not only is this a nice way of writing down linear transformations and not having to check that they are linear, it's also a unique description of any linear transformation, right? So these linear transformations that look like this are in fact the only types of linear transformations that there are, right? So any linear transformation that we could write down will be of this form, right? Okay. And let me say something about this EI, these E1, E2 up to EN. So here, this EI is the vector in Rn. Or, oh, wait. Vector in Rm, sorry. With 1 in its ith entry. And zeros elsewhere. Right. And another way of describing this is to say that so another way of describing EI is to say that EI is the ith column. Of the identity matrix, which is how it's stated in the book. Okay, so what is an identity matrix? It is just, so I'll give a couple of examples. So in 2 dimensions, we would get 1, 0, 0, 1. If we have 3, so we just have, basically you have ones along the diagonal. So moving from the top corner, top left-hand corner to bottom right-hand corner, that's the diagonal. So you have ones along there and everything else is 0. And so in general, so we use this n to denote how large the matrix is, right? So if we had n, then it would be 1 zeros underneath it, 1 and some zeros, something like this, right? So we can form a matrix in this way. This is what is referred to as the identity matrix. And the reason it's called the identity matrix is that if we take it and multiply it by a vector x, it will give us back x, right? Okay. So you could check this by looking at, let's say 1, 0, 0, 0, 1, 0, 0, 0, 1. And if you do the matrix multiplication, you get x1, x2, and x3 back. Right? So it doesn't change it. Okay, so next time we'll talk more about this idea and do a quick proof of this theorem. Right, so, and then finish up with 1.9. Okay, so are there any questions or is everything good so far?
Will you post like you did before what we should study for the quiz?
Oh, right, yeah, quiz. So we don't have class on Monday. I should have, yeah, mentioned that.
Wait, oh, huh.
Yeah, so we have a break day on Monday, so we only have class once next week. I guess I was considering not doing a quiz next week. I haven't decided yet, so I guess I'll post an announcement with that info. But definitely won't be till next Thursday. And oh, so for the problem session, I don't know how many people would be able to join. So we have Thursday, Friday, Thursday. So I think it'll be Thursday. I can let Micah know and you guys can have the problem session today. I don't know how many of you have already looked at the problem session problems. Would anybody show up if it was held today? No, can't do today. Okay. Anybody interested in problem session today?
It'd be in the evening, right? It'd be around
4.
4. Okay. That I could probably make. Yeah.
Okay. So I'll tell him and you guys can show up. And then we'll start doing this regularly. Next week, since we don't have class on Monday, it will be the only problem session time. So hopefully if you want to go, you can make that time. So it'll be Thursday. Let me write this out.
There also Monday, didn't you have one on Monday too? So
Yes, but and then regularly we'll have Monday 4 to 5 p.m. but not next week because there's no classes.